Good morning, everyone. Welcome back to day 2 of 5.1 when we started learning about the transformation. So yesterday we talked about the transformations dealing with a horizontal or a vertical shift, up or down, left or right. Today we're going to continue with the transformations, and we're going to be looking at the stretch or compress and reflection, dealing with graph and how or what is going to cause those graphs to have a stretch or a compression or a reflection. And we're going to be doing the triad problems throughout. And let's take a look at the first example here. So what causes a graph to be stretched or compressed? In the general equation, we have g of x equals f of x, but if we multiply f of x by a number in front of it, we call it a in this case. So if we let a equals 2, what is it going to do to the graph of f of x? So here is again the original f of x function, and if we take the values of f of x, which is right here, multiply it by a number. In this case, we're going to let it be 2. So let a equals 2. So it's like saying 2 times f of x. So we're going to take 2 times every single one of the values of f of x. So let's take a look at the first one. 2 times negative 2, that gives us negative 4, is already done for us. And then 2 times 2 is going to give us 4. Next, we're going to do 2 times negative 2 again, which is negative 4. And then 2 times 2 is 4. So these are the new values. And we're going to take the original x and map it up with y to make the new point. So negative 1, negative 4 is here. 1, 4 is going to be here. And 3, negative 4 is here. And finally, 5, 4 is here. So again, if we follow the same pattern, the graph of which is in the shape of like the letter N, we are going to have this new graph, which looks something like this. So if you compare that with the original, it kind of looks like the graph is actually stretched out, which means like it's taller than the original. So now we can conclude from looking at the graph that when the number a, which is in front of the value, the f of x function, is greater than 1, so when a is greater than 1, we are going to have a what? What did we say it was? A vertically stretched. So this is a vertical stretch. And we say that there is a vertical stretch factor of 2. Okay, so vertical stretch factor of 2. And that is the effect that a number in front of an equation would do to the graph. Next, we're going to take a look at when the number is not greater than 1. So a equals 1/2 in this case, which is smaller than 1. And if we look at that, we are going to see that when we multiply, that taking the function of f of x, multiplying by 1/2 is going to give us negative 1, half of negative 2. So we're going to multiply everything by 1/2 here and see what happens. So that's going to be 1, and here is going to be negative 1 and 1 again. So here we have the new point, negative 1, negative 1, and then 1, 1, and then 3, negative 1, and then 5, 1. So if we connect those points again following the same shape, you will see that the graph is actually compressed. So we have a conclusion that if a is between 0 and 1, which means it's less than 1. So if a is less than 1, or just between 0 and 1, which is a fraction, we are going to have a vertical compression by a factor of 1/2. And that is the transformation that is associated with multiplying by 1/2. And let's take a look at the next one. We're going to multiply the x value instead by a number. And in this case, this is a little bit tricky, notice that the b, the factor that is being multiplied, is underneath the fraction because that's what the original equation would come in. So it's 1 over b, which is 1/2. And so in this case, we're going to have f of 1/2 of x. And notice that again, b is actually equal to 2 in this case, even though it looks like it's a fraction. So we're going to multiply the x value by 1/2. So 1/2 of -2 is -1. 1/2 of 2 is 1. And so if we need to think about 1/2 of what is going to give us 3, the answer should be 6. So we have 6 is the value that we need in the next box. And then finally, 1/2 of what is going to give us 5, and the answer is 10. So now if we graph the new values of x with the original y's, we should get the new points. So -2 and -2, which is here, and then 2, 2 is here, and then 6, -2 is here, and finally 10, 2, which is going to be like off the chart somewhere over here. So if you take a look at that and connect those dots, we are going to have actually a horizontal stretch. Look at the graph. It is stretched horizontally. So when b is greater than 1, notice that again, just because b is underneath the fraction, it's still greater than 1 in this case. So b is greater than 1. This is a horizontal stretch factor of 2 in this case. And that is the end of that problem. And let's take a look at the discussion question. How would you expect the graph of g of x to be related to the graph when b is a number between 0 and 1? So in other words, when we have b between 0 and 1, which means like a fraction, for example, 1/3, what would that look like? Then g of x is going to look at 1 over 1/3 times x, right? F of 1 over 1/3. So that's going to be f of, believe it or not, 1 divided by 1/3 is actually 3 because it's 1 divided by 1/3, which means 1 times 3 over 1. That's how you get 3. So it's f of 3x in this case. And in this case, the conclusion is that the transformation is going to be a compress. It's going to be a horizontal compression by a factor of 3. Okay, actually factor of 1/3 because that is less than 1. So it's 1/3. So 1/3 is actually b in this case. So b equals 1/3. And that's going to cause the graph to be horizontally compressed. So instead of looking maybe like this, it's going to be like this. It's compressed. So it's going to be all crunched together horizontally. And that is the end of the lesson. And for that part, and we're going to actually take a look at the next thing, which is going to be for what happens when we have a number that is negative in front of the f of x. So for example, if a happens to be -1, so we're going to just have negative f of x. What does that do to a function? So if we are just multiplying the function right here, the value of y by -1, so look at what happens when we multiply -1. Negative is positive. And we have -2, so -2 is 2, and -2. So let's graph those x values right here with the new y. So -1, 2 is -1, 2 here, and then 1, -2 is here, and 3, 2 is here, and then 5, -2 is here. So if we connect that, we should have the letter n flipped. So this tells us that if there is a negative sign in front of the f of x, it means that there is a reflection across the x-axis. So it's been flipped based on this line right here. So if this is a mirror, then it's a reflection of the original. And that is what a function does when there is a negative in front of the f of x. And let's take a look at this right here. If b is negative in this case right here, which means we have just f of negative x. So again, if x is the one that is going to be applied the negative, which means x gets to multiply -1, we're going to have multiplying by -1 here. So what times -1 gives you 3, which is -3. And then here, -5, right? So if we graph these right here, the x value for these x values, we're going to have 1, -2. So here, and then -1, 2. And then -3, -2. And -5, 2. So if you connect that, you will have a reflection across the y-axis, meaning this is your mirror right here. So this is the reflection line right here. And that is what it looks like when we have a y-axis reflection. And that sums up all of the transformations that deal with the horizontal and vertical stretch and reflection. So here in conclusion, we have the reflection in the x-axis when there is a negative in front of the f of x, and if there is a negative inside, then we have a y-axis reflection. So if it happens outside the function, it is x-axis. If it happens inside the function, then it is y-axis. And here are some notes again. A function is even if when you substitute the negative inside, you're going to get the original back. So for example, if I let f of x equals x squared, and I substitute negative inside for x, I will have negative x squared, but then when I evaluate it, I'm going to get x squared, which is the original back. And that tells me that the function x squared, y equals x squared, is an even function because I get the original back when I substitute negative inside. And so if I have a negative, so if I let y equals or f of x equals to x cubed, and I substitute negative x inside, I will have negative x to the third. Well, that gives me negative x cubed back. And notice I have the opposite of the original. So that tells me that x cubed is an odd function. So hopefully that demonstrates what an odd and even is. You really need to just substitute negative x inside for x to see what you get back. And that takes us to the discussion questions. On the coordinate plane, what is the difference between a vertical stretch and compression? So if you have a function, f of x, if you have a vertical stretch, if you have a in front of it, when a is greater than 1, you're going to have a vertical stretch. So that's a vertical stretch, vs. And if you have a is between 0 and 1, then you're going to have a vertical compression. And right here, VC stands for vertical compression. Okay. And then on second question, what is the difference between a horizontal stretch and a vertical stretch? So again, if you have f of x, a number in front of the function is going to be a vertical stretch. So that's how you can tell. And then a horizontal stretch is if you have the number 1 over b and apply to the x value. That is how you're going to have a vertical, and when b is greater than 1, that's how you're going to have a horizontal stretch. And that's the difference between the two. One is applied to the outside, so this is outside, and one is applied to the inside. So that's how you can tell the difference. And so we have a definition here to help clarify. A definition is for a function is even if the graph is symmetrical with respect to the y value. So it's even if it's something symmetrical, like, you have the same values here. So this would be an example of an even function. And then, or in algebraically, you can, like what we did, substitute the negative x inside, And if you get the same value back, then you're going to have an even function. And it's odd if the graph is symmetric with respect to the origin, for example, something like this. So you're going to have like opposites here. So that's the odd function, okay? And that is the end of the lesson for today, for day 2. So go ahead and get started with your homework in Google Classroom and finish your assignment for today. Have a nice day.